Well, today we're going to do two very geometric techniques for doing three-dimensional integration problems. And one of them is a parallel to polar coordinates, but in 3D, and the other one is going to involve spherical things. Okay, so we know what polar coordinates are in 2 dimensions. So in 2 dimensions, I'll do polar integrals, let's say, and make sure you're muted, please. We know in 2 dimensions that we're always going to replace x with r cos theta and y with r sine theta. And then the dA in xy world is going to become r dr d theta in the polar world. So when we have the double integral over the region in the xy plane, and we'll write it like this, we'll say f of xy dA, we know that becomes, it's the same region, okay, but we redescribe it with r and theta, and we kind of loosely say now it's r, and then we do this, and it's the same region, but let's say r theta region. And we get fairly good at this. Most of you did a really nice job with the integrations in general, and on the last quiz, when the surface area problems, people were doing a really nice job of converting, but that's 2 dimensions. So what happens if I want to do a 3-dimensional integral? Well, it turns out 3 dimensions is wonderful because very little changes. So the first thing is we call this cylindrical coordinates. And what cylindrical coordinates are basically polar coordinates in 3D, where x is still r cos theta, y is still r sine theta, and z stays z. You don't do anything to z. So essentially, if I have an integrand that involves x squared plus y squared in some capacity, or my region in the xy plane is circular in nature, but I have a roof, then we'll do this. So let's do a really simple example of one of these. Let's suppose I'm looking at the circular paraboloid f of xy equals x squared plus y squared. Turn that off. And let's say the plane z equals, how about z equals 36. Okay, so what that looks like, oh, so we know what this looks like, and I'm bounded by the plane, if you will. Okay, so hopefully that you can kind of see what's going on there. I've got this guy that's opening upwards, the circular paraboloid, and then I'm slicing it with the plane z equals 36 and creating this gumdrop, basically, this bullet shape. I would like to find the volume of this thing. Now, I have no doubt that I could set it up correctly in xy, but that might make it a really nasty integration. So in xy world, my volume would be the double integral over the region in the xy plane. Now, how do I set it up? Well, I'm going z equals 36 on top and z equals x squared plus y squared on the bottom. So my integrand would be 36 minus x squared minus y squared. Okay, so this is exactly what I would get. Now, I can easily integrate this. There's nothing tricky about this integrand. The tricky thing is about my region in the xy plane. Now, here's the thing. First of all, what is the region in my xy plane? I mean, I'm intersecting at the origin. So here's what you're doing. You're standing way up top. You're standing on the z-axis, balancing, you don't want to get impaled by the, sharp point. And you're looking down, and even better yet, close one eye so you don't have any depth perception. When you're looking down, you're going to see that circle. In other words, when I project down, that circle is my region in the xy plane. So if I project it down, that's what I'm going to see. That's what I'm bound by from xy, because this plane here is parallel to the xy plane. There's no z now. So what circle actually is this? Well, it's the intersection of this and this. So it's the circle x squared plus y squared equals 36. So that's my region in the XY plane. Now I can definitely do this as a circular region, right? I'd have Y and X going from plus and minus roots and nasty stuff. Or I can simply switch it to polar. So how do I do this in polar? Well, if we were going to do this in polar right off the bat, that would have been a piece of cake. But how would I have done this if I wanted to set this up as a triple integral? And that's what I want to do here, is I want to think of this as a triple integral because we're going to then integrate with densities and other things. So I already know how to do this now as a double integral. So if I back up, let me change this. So if I back up then, my phone keeps ringing here. Then my Z, okay, my Z is going to go from the lower Z, which is this guy, to my upper Z, which is this guy. Okay, and this, I'm going to still call this my region in the XY plane, this thing. Now you say, well, but I thought we don't do volumes with triple integrals. No, we don't do volumes with triple integrals. But when I switch over to polar, I'm going to have an extra variable anyway. So right now, we would just say this is 1 dv, or this would be probably dz dy dx or dz dx dy. So when I switch to spherical coordinates, or excuse me, cylindrical coordinates, sphericals later, I will do this still as the r theta, but the z is going to now become z equals r squared to z equals 36. This is going to be for the r and the theta. Remember, it's a circle of radius 6. So 0 to 6, 0 to 2 pi. And my integrand now becomes r dz dr d theta. Now, I don't put the r on the other side. I'm going to integrate z first. And so this looks very much like what we did before, but I'm going to need to do this as a triple integral. Okay? So when I stare at this thing here, still r dr d theta, but I'm integrating z first. Okay, that doesn't affect the, that will have no effect on the r. But now this will give me the volume because now I've changed it to polar basically right from the get-go. So
where did the 6 and the 0 come from?
That's theta and that's r.
Oh, r. Okay, okay.
Yeah, circle of radius 6.
So then the 36 and the r squared would be z. That's what we just moved, right?
So this
Yeah.
became that.
Okay.
Boom. Yeah. So this is because I'm now r and theta. Do you notice I don't even bother with the XY limits? If you know you're going to convert, don't even bother figuring out what the XY limits are because you're never going to do it. You're going to do polar all along. Now we loosely say polar. Technically, it's called cylindrical because it's 3-dimensional. Polar is strictly 2-dimensional, but it's polar in the XY plane, and then Z stays Z. So let's go ahead and do this. I'm going to erase this so we can see. If you don't mind polar, then you don't mind this because it's not any harder. So my first integration is going to leave me with 0 to 2 pi, 0 to 6, RZ, where Z is going from R squared to 36, and then dr d theta. So this would be the proper order of things. Now I'm integrating the Z, so these guys go in for Z. So I'd have 36r minus r cubed dr d theta. Now this becomes a fairly simple problem. 36r minus r cubed. Now integrating with respect to r, you have 18r squared minus 1/4 r to the 4th from 0 to 6 d theta. And what would that give us? That will give us 18 times 36. So that would be what? 648. And then here that'd be minus 324. Well, that's just 324. Because my limits are constant, because my integrand is constant, then all I gotta do is take the difference of the limits. Some of you tried to do that on the last quiz. I like it when people are trying to take shortcuts, but the whole multiplying by 2 pi, I can only do if this is constant. If there's a variable in here, I can't multiply by the length because it's still have a variable. So my answer is gonna be 2 pi times this. This is kind of nice. Now, I can find all sorts of things, but the idea is I have a 3-dimensional problem. I'm probably trying to find a volume, or might be a center of mass problem. We're going to do that in a moment. I have either a circular region in the XY plane, or I have an integrand that involves x squared plus y squared, maybe to various powers, maybe like the square root or something, where I'm looking at that going, this is going to be really difficult in rectangular, but it's a really smooth problem in polar. So that's kind of where this goes and where it comes from. There's really no ambiguity. Now, could I use this to find the volume of a sphere? Yes, I actually could, but there's actually a better way that we're going to do next. Okay, the second part of the class today. So let's do an example. Now, normally when I teach Calc 3 in the fall, this late in the semester, we're getting closer and closer to Thanksgiving. And so the analogy that I use is actually very appropriate at the time. You see, a lot of you for Thanksgiving, I don't mean to make you hungry by any chance, but you have cranberries. A lot of people have cranberry sauce. Now, my wife makes homemade. She uses the Cuisinart and does, it's off the charts. But some people buy those nasty cans of cranberries. And in the nasty can of cranberries, when you open up the can, you'll notice it's liquidy at the top and it gets more dense as you go down. And by the bottom, it's very thick and sludgy and kind of disgusting. Okay. But that can of cranberries is not uniform in its density. In fact, very few things are. I mean, a can of water would be uniform in density, but that would not be uniform in density. The example I like to use in class is, let's suppose that we took the classroom and we just filled it up with Jell-O. Made gelatin, okay? That's probably going to be uniform in density. But what if we threw a bunch of fruit or a bunch of stuff in the Jell-O? It's probably all going to settle at the bottom, meaning the density would no longer be uniform. In fact, we tend to think of anything that's not pure liquid is going to be more dense at the bottom because stuff settles. Heck, your orange juice, if you go in the fridge, if it's been sitting for more than a day or two, it's probably got the pulp all settling at the bottom. So what we want to talk about is, how do you determine the center of mass, particularly like of a canned good, that is not uniform density? So here's what we've got. We've got a can. Let's keep it real simple. We've got a can. Let's say that the radius is 10 centimeters, and let's say the height is, 20 centimeters. Keep it simple. Okay, it's a kind of squatty, almost squarish looking can. Now, it's whatever's in there, that's great. I want to find the center of mass of whatever's in there. And what we're going to assume is that the density increases as I go down. So it's very dense at the bottom, not very dense at the top. Again, probably watery at the top, thick and sludgy at the bottom, kind of gross. So let's say that the density, which now would be a function of x, y, and z. This is what we did last day, by the way. Let's say that the density is simply, how about 10 over z plus 1? Meaning when z is 0, I'm at the very bottom, z is 0. I'd have a density of 10 whatever. In this case, it'd be mass per unit volume. But at the top of this can, when it's 20 centimeters high, the density would only be 10 over 21 of whatever the units are. So in other words, this density, very low when I'm high, very high when I'm low, okay? I'd like to know where's the center of mass of this. Notice the density doesn't change left to right. Well, that actually makes sense. If this can were empty and I'm just pouring stuff, maybe I'm pouring soup. I mean, it could be soup. I'm pouring stuff into the can. We know that stuff, when it spreads out horizontally. Stuff doesn't spread out vertically. I've got all my stuff, it's spreading out horizontally. So as I move horizontally, it makes sense that the density stays the same. As I go vertically, the density is less because gravity has pulled all the heavy stuff to the bottom, and it's basically watery at the top. I want that to be clear to make perfect sense to you. So the density doesn't have X or Y in it because, again, it shouldn't really change this way. So I need to do some integrations. Well, I have kind of a problem here. I don't have any equations. In fact, I just have a can. You know, I have my can. When you walk outside, I'm pretty sure you're not going to be able to see the X, Y, and Z axes. You're not going to be able to see the three-dimensional grid to set up your problem. No, we need to create it. So why don't we do this? Why don't we create it in such a way that this can is centered on the Z-axis with its base on the XY plane? That would be the most logical setup. So I've got the can looking like this. Okay, that's not too bad of a drawing. So you guys can all see what's going on here. The base is on the XY plane. Now, what is the equation of the base? This is a circular cylinder. So the equation would be, well, I have a circle of radius 10. So wouldn't this be x squared plus y squared equals 10 squared? That's the equation of my circle. And I'm bounded between z equals 0 and z equals 20. So I have a right circular cylinder. It's not infinite. It goes between z equals 0 and z equals 20. So now I've been able to describe my shape and give it an equation, because I need to set up some integrals, and I kind of need this stuff in order to be able to do the integrations. Okay, so when I'm looking at this, we have three integrals, remember. We're going to have the mass and the three moments. So we'll do them all one at a time, and then we'll look at the final answer. And the final answer, now, if somebody had to just guess, you know, this could be a large building, a large, you know, circular cylindrical building. If the heaviest stuff is at the bottom, would I expect the center of mass to be above the midpoint on the z-axis or below the midpoint on the z-axis? Anybody? What do you think?
Below.
Probably below, because if the heavier stuff is near the bottom, we would expect the center of mass to be lower, which would actually be a really good thing for balance. It would be harder for this thing to tip over. That's one of the benefits. Okay, so how do I find the mass? Little m. Well, little m is the triple integral over the volume of the density dV. Okay, now, because this is a circular cylinder, I think it's pretty safe to say that we will use cylindrical coordinates. That's kind of the no-brainer in this case. We're going to use cylindrical coordinates. I have to do a triple integral. There's no way around it. So that means polar in x and y. Now, that's not changing, but because I'm switching to cylindrical, I'm going to have the r dz dr d theta. Okay, now what are my limits of integration? Well, let's start with the z. That should be easy. Z is ranging from 0 to 20. R, this is a circle of radius 10. So R is 0 to 10. And I'm going all the way around, so 0 to 2 pi. Okay. Now that doesn't look like a horrible integration. So let's do this. So when I do my integration, I'm integrating with respect to z. Oh, forget the r for a moment. 10 over z plus 1. What would the antiderivative of that be? Anybody? What function? The z is on the bottom.
Natural log.
Natural log. Good. So this is good. The 10's not going anywhere. So this would be 10 log absolute value of z plus 1 times r, evaluated from 0 to 20. I'm going to have to, unfortunately, now erase my beautiful drawing. Dr d theta. What I'll do is after every integral, I'll just put the results up there so we don't lose anything. Now, this is actually not bad at all. This is going to be quite nice. Okay. When I replace with 20, this is going to be 10 times the log of 21. That's just a constant. Minus 10 times the log of 1. What's the log of 1?
0.
0. Love log 1. It's my favorite log. It's the only one I can't mess up. So I have 10 log 21 r dr d theta. Okay, 10 log 21 is just a constant. It's going to show up in the final answer as a multiplier. So don't be intimidated. Yeah, it might be ugly, but that's what it is. So I'm now going to have 1/2 r squared. So that means 5 log 21 r squared. From 0 to 10 d theta. So when I evaluate r squared from 0 to 10, I'm going to get 100. So now I've got 0 to 2 pi of 100 times this. So that would be 500 log 21 d theta. And since that's a constant, I just multiply by the 2 pi. So I now have 1,000 pi log 21. What a crazy answer, right? So I'm going to write that up here. So our mass is 1,000 pi log 21, whatever that is. Now remember, when after I find my moments and we find the center of mass, that's going to end up being the denominator for x bar, y bar, and z bar. So hopefully we can get some canceling and maybe it comes out a little bit simpler. So now let's do the different moments. Unfortunately, I can't use any of this because I'm going to have another variable be multiplied. So the integrals will actually all look a little bit different. I'd love it if I could just use these answers, but I really can't. So let's start with how about the moment that involves the x distance? So that'd be the moment to the YZ plane. And that now I'll use capital. Okay, is there a multiplier? This is the distance to the YZ plane.
X.
X. Okay, and then dV. We haven't gone polar yet, so I got to put that X in there. So now when I go polar, that X is going to become r cos theta, isn't it? Oh, this is definitely a little bit more complicated than the previous. So when I do this, okay, we now want to go polar. This is going to be 10 over z plus 1. This is going to be r cos theta. Then I'm going to have r dz dr d theta. Okay. My z limits, oh, by the way, all of my limits should be exactly the same. Because the only thing that's going to change is my integrand, not my limits. So let's rewrite that because we have an r squared now. So now let me write it this way: 10 z plus 1 r squared cos theta dz dr d theta. There we go. My first integration again involves the z. And since there's no other z there, that's just going to be a natural log again. So I'm going to have 10 ln absolute value of z plus 1 r squared cos theta z evaluated from 0 to 20. So this is going to look like the other problem, this part here. So when I evaluate at 20, I get log 21. When I evaluate it at 0, I got log 1, which is 0. So we'll just go ahead and take advantage of that now. So this is 10 log 21. R squared cos theta dr d theta. So 1/3 r cubed. So I'll write that as, how about 10 log 21 over 3. There's my third. R cubed from 0 to 10 d theta. Okay, this looks kind of treacherous, filled with treachery and other things. That's going to be 1,000. I already had a 10, so now that's was it 10,000 thirds log 21. Whoops. Oh, I lost something. Sorry, I lost the cosine. Whoops. That no work. Sorry, need that cosine theta in there. There we go. So 1,000 thirds log 21 cos theta d theta. There we go. And of course, we know the antiderivative of the cosine is simply the sine. Now I can't multiply. I have a function here. I have to integrate. So this will be 10,000 thirds log 21 sine of theta from 0 to 2 pi. Great. And wait a minute. What is that value? Sine of theta from 0 to 2 pi? Well, sine of 2 pi is 0. Sine of 0 is 0. So that answer is 0? No, I guess that's what we get. We'll make sense of it later. How's that? Yeah, 0. I'll put it right underneath here. I have to write a little bit smaller. So m yz is 0. Okay, I'm going to write it there so I can erase the rest. How interesting. All right, well, let's find, how about we find m, well, let's do the one with the y distance, okay? So that would be, the one with the y distance would be mxz. And then what do I multiply this one by? What do I multiply by here? Couldn't hear. What was that?
Y.
Y. And you notice we do this before we change it to polar. You can't change it to polar and multiply it by y because I'm going to have to convert the y into polar. Well, this is going to look very similar to the last one, obviously. So when I convert this, again, 0 to 2 pi, 0 to 10, 0 to 20, 10 over z plus 1, r. We know it's r sine theta times r. So let's just go ahead and write r squared sine theta because we did that last time. Now we know it's going to be an r squared. dz, dr, d theta. Okay. So we do the z integration first, just like before. I think we're getting used to this one. So I'm going to get 10 log z plus 1 r squared sine theta from 0 to 20 dr d theta, which I think I can probably fit on this line here. We already know that's going to be 10 log 21. R squared sine theta, dr d theta. Okay, it kind of got it there. All right, little tight. So now we're going to integrate with respect to r. So this is going to look again like the last one, a lot of the same terms in the same place. So we're going to get 10 log 21 over 3 r cubed sine theta from 0 to 10 d theta. And like before, that's going to be 1,000. So that's 10,000 over here. So 10,000 log 21 over 3 sine theta d theta. Now, when we integrate the sine function, we're going to get the negative of the cosine. So this will then be negative 1,000 log 21 over 3 cos theta from 0 to 2 pi. Aha, because cosine of 2 pi is not 0. Cosine of 2 pi is 1 minus the cosine of 0, which is also 1. And therefore our answer is what? Could it be 0 again? Wait a minute, how could that be? Got 0 a second time? You don't suppose that the last moment's also going to be 0, do you? That would probably be bad if it was, because then that would mean our center is the origin. I don't think that's going to happen. Interesting. We'll make sense of that in a moment. All right, last round. Okay, now we want to do the moment to the xy, which of course involves the z distance. So that, as you all know, is going to be z dv. Oh, that presents a slightly more complicated integrand now, because I got the z on top and on bottom. We'll figure that one out in a minute. So when I switch to polar, which I have to, I can't do this any other way. Right now I have 10z over z plus 1 dz, r, sorry, I'm losing my r, r dz dr d theta. Now, how to integrate this guy? Well, it's actually not that hard. I may want to factor the 10. I may want to take this 10 and just put it on the outside. It might be in the way. You see, I can do long division, I can do synthetic division, or I can just simply do that, in which case it's 1 minus 1 over z plus 1. I prefer that, it's just easier. So z over z plus 1 is equal to this. You do a quick check. Oh, and this is easy to integrate. Again, I'm going to get a log in there. So this will become, actually, I'll put it over here. And I'll leave the 10 out in front. It's not going to cause any problems. One minus 1 over z plus 1 r dz dr d theta. Sorry, that was a little squished in there. So now when I integrate that bad boy, I'm going to get 10. Okay, the integral of this z minus the log z plus 1. Actually, let me use parentheses, sorry. Because I still have the r. Now I'll bracket it off. And I'm going from 0 to 20. Oh, definitely have an extra term in here that I didn't have before. Dr d theta. So when I evaluate this at 20, I'm going to get 20 minus log 21. When I evaluate at 0, I'm going to get 0 minus log 1, which is also 0. Okay, so this is my only coefficient that's really remaining. R dr d theta. Okay. Sorry, it's hard to read. Now when I integrate with respect to r, I'm going to get a half. I'll just go and combine that with 10. So I'm going to have 20 minus log 21 r squared from 0 to 10 d theta. Well, I'm not cubing the r this time, I'm only squaring it. So I'm going to get 100 times my 5. So now I have 500 times the integral from 0 to 2 pi of 20 minus log 21. And I like where we are now because that's a constant. I'm going to take the difference times that times that. Yikes. Well, the difference would be 2 pi. 2 pi times 500 would be 1,000 pi. So this is going to be 1,000 pi times 20 minus log 21. And I'll just go ahead and leave it like that. Yes, of course you can distribute. Or you can just leave it. Either or. All right, so that gives us our last moment. And our last moment was most definitely not 0. Put it up here. Now, we need to find our center of mass. So what we know that x bar is the moment to the YZ axis over little m. We know that y bar is the moment to the XZ, I said axis, sorry, plane. And we know that z bar is the moment to the XY plane over little m. So what's x bar? 0. Huh. X bar and y bar are both 0. Interesting. And what's z bar? Z bar is this quantity here. Actually, let's do this. Let's go ahead. Oh, no. I'll leave it factored. Sorry, I was going to say let's go ahead and distribute, but we don't really need to. Here's why we don't need to. See something very nice happening right about now? Yeah, huge canceling. Well, obviously, the 1000 pi cancels. And now what I've got left, I can certainly split up. And it looks like that's just going to be 20 over log 21 minus 1, which I think is probably the simplest answer. So our center of mass is going to be at 0, 0, 20 over log 21 minus 1. Now, I have no idea how big that is. Let me get on my calculator. All right, so 20 over log 21 minus 1. Interesting. That's about, it's about 5.57. Let's go back to what our can looked like. Our can was 20 centimeters tall. So if I stick a z-axis right through the middle, it means that our center of mass, first of all, is on the z-axis. Now, does that surprise us, or should we really have expected that? Anybody? Our center of mass is on the z-axis that runs right through the middle of the can. Should we have expected that?
Yes.
Of course you're supposed to. Of course we're supposed to expect that. Remember what I said about density? Density doesn't change horizontally. It only changes vertically. Oh, so if it doesn't change horizontally, then think of a circle. Then the center of mass of any circle should be right at the center of the circle. The z-axis runs right through the center of the circle. So that makes sense. See, if the density had changed left or right, then that would have affected our answer. But the density, remember, the density was purely a function of z. So we ended up getting 0 for both the moments involving the x and the y. So those coordinates were 0. We really should have expected that the center of mass was directly on the z-axis. Now, when I said, do you suppose it's in the top half or bottom half? You guys said, no, it's probably in the bottom half. It's way in the bottom half. I mean, this is almost the bottom quarter. Okay, so as I move up the z-axis, it's way down here, which is a good thing. So from a balance standpoint, if I'm stacking cans in the grocery store, if I have cans like these nasty cranberries, okay, where the density increases as I go down and it's really heavy at the bottom, but really light at the top, then those cans don't tip over very easily. Now think of a car. Where's all the weight of a car? Is it in the top half of the car?
Bottom half.
Yeah, I mean, the top half of the car is mostly air. I mean, think about it. Think of where you're sitting and now go all the way to the roof. That's just mostly air. But below your seat, now you have all your frame and you have everything else, all the heavy stuff. That's a good thing because it means the car is going to be harder to tip over because the most of the weight is at the bottom of the car. So if you thought of how high does your car sit off the ground? Okay, so go halfway to the ground and my centroid should be about that height. No, the centroid is probably way lower than that. And that's a good thing. Tall buildings, the centroid should be way lower than the halfway point going up. Wind, earthquakes, things of that nature. So this is an exposure to cylindrical coordinates. It's basically just polar in 3D. Now we're going to move on to the next one, which is very, very specialized. The next one is what is called spherical coordinates. And this is very specialized. This would be basically, I'm bounded by a sphere and maybe I have different density, or my integrand involves not x squared plus y squared, but x squared plus y squared plus z squared, which is what a sphere typically would look like. Okay, so I'm going to give you a little picture and then I'm going to develop the integration part. So some of you may have done something like this before, but in all likelihood, maybe not. Now, if you remember, when we talked about spheres first day of class, a sphere generally is in this form: x minus x0 squared plus y minus y0 squared plus z minus z0 squared equals rho squared. We generally don't use an R with a sphere because the R is kind of mentally, we think of that as the two-dimensional circle. So when we use an R, that was the radius of the circle. But when we were in 3D, we generally used a rho, which is the Greek R, by the way. And that was sort of our generic sphere. What happens if we have a sphere centered at the origin? Well, then we just write it like this. Okay. Now, in this case, we're going to use rho. Eventually, rho is going to become a variable. It's kind of like in polar, we're using R as a variable, not as a value. So what I want to do is talk about the relationship between a point in XY, a point in polar, and then a point in spherical. So let's suppose I go out to this point right here, which we will call, this will be X, Y, Z. Okay, this is just some point X, Y, Z. Now, I've gone out from the origin, I'm out in space. Okay, I'm not on one of the planes, I'm out in space. So first of all, this distance here, this is rho. Okay. The angle that I'm going to make with the Z axis is called phi. Phi is this way. Theta is this way. Or if you do it on a computer, you do this. Now, I know some of you make your zeros that way, and I still haven't figured out why any human being would make a zero with a line through it. But I'm a math guy. Zero is, the shape of a capital O. But anyway, that's the angle phi. Phi is the angle made with this line segment, right? This line segment is coming out. It's the angle made with the line segment and the Z axis. Nothing to do with the XY plane whatsoever. Now, what I'm going to do is I'm now going to project this point down onto the XY plane, and let's say it projects right to there. So that point on the XY plane would be the same X and Y, but it'd be XY 0. So I have a point out in 3 space, and now I'm projecting it down to the XY plane. But now when I draw the line segment this way, that is R. See, this is on the XY plane. So that distance is exactly what R is. And this angle right here on the XY plane, that's a terrible thing. That's theta. Theta and phi are completely unrelated. Theta is the angle on the XY plane made between R, and that's the x-axis. Phi is in 3D between the z-axis and wherever you are. Okay. Now, let me finish off the rectangle. So if I then project back up to the same way, okay, that was a terrible projection. I'm sorry. These are supposed to be parallel. Now, we know that there's a right angle. It's hard to see. There's a right angle right here, because that's straight down to the XY plane, and then that's on the XY plane. These are parallel. So then there's a right angle right here as well. Okay. And that's hard to see. So I have a right angle here. I have a right angle there. There's a right angle there. There's a right angle here. So basically I have a rectangle. This is a rectangle that's coming out at you. So then what are the other pieces of my rectangle? Well, if that's R, then that's also R. From here to here, that's exactly Z. Remember, this point was X, Y, Z. So when I project it back to the Z axis, so hopefully you guys can all get an interpretation. So I have this point in 3 space. When I go straight back to the Z axis, Now that point would be, on the z-axis, that point would be 0, 0, z. Same z. This would be x, y, 0. Now that I've got all of these, I have some wonderful relationships between the stuff going on here. So first of all, look at that picture right there. The sine of phi, think SOHCAHTOA, right? The sine of phi would be r over rho. Which means quite simply then that r equals rho sine phi. How about the cosine of phi? Again, think SOHCAHTOA. The cosine would be z over rho, which means that z equals rho cosine phi. Okay, so I'm trying to set up the relationship. Now, finally, we know that x squared plus y squared equals equals r squared. We know that. Okay, from the polar world. So that statement right there tells us I could also write this as r squared plus z squared equals rho squared. That would be the Pythagorean relationship between r and rho. There we go. But that's not the one I want. The one I want is going to involve x and y. I now have a way of writing z. You notice there's a rho and a phi. There's no r's and thetas. I want to write x and y without using r and theta. So we know that x equals r cos theta. We know that. But since r also equals rho sine phi, that means that x is rho sine phi cosine theta. We've just figured out a way to write x without using r or theta. We know that y is r sine theta. But if I use this, then this becomes rho sine phi sine theta. So this is x, this is y, this is z. These are called spherical coordinates. Okay, I'll write it down here. Spherical coordinates. Now, are there any restrictions? Well, rho, like r in polar, rho is generally going to go between 0 and the outermost part of the sphere. Okay, so rho is not going to be a negative value. R generally ranges from usually from 0 to, again, the outer part of the circle or whatever shape you're dealing with. Now, theta is still the same theta. Theta is still going to have a range potentially of 0 to 2 pi. But what about phi? What about phi? Let me grab something straight here on my back scratchers. Okay. Because my own arm is not flexible enough. So here's the z-axis. Okay. Now, this might be how I'm going. Now, from here, can I go 360 degrees if this is the z-axis? Okay. So this is coming out at you, so I'll turn it sideways. So here's rho. Rho is now on the xy plane. Rho is now pointing straight down. Phi is the angle between rho and the z-axis. Do you notice? That can only go from 0 to pi. There's no coming back around. You see, as theta moves in a circle this way and phi goes this way, then I can carve out every point. So give me a particular phi, now I'll go around in a circle. Give me a different phi, now go around in a circle. Give me a different phi, the bottom half of your sphere, if you will. So phi, the most that phi can range is 0 to pi. The most that theta can range, we know, is 0 to 2 pi. So that's a really cool restriction. Because again, phi is defined as the angle made with the z-axis. But the z-axis goes from here to here. It's only a 180 degree swing, not a 360 degree. But theta does go all the way around. Okay. So now the last piece of the puzzle we need, which I usually derive in a classroom situation, but I lack some of the tools to do this on Zoom in 2 dimensions.
I didn't really get what you just said right now with the pi and 2 pi. I'm sorry.
You mean phi?
Why is it range to 0 to 2 pi? I mean pi, sorry. The phi.
Because I have the z-axis.
Mm-hmm.
Okay? If it helps, think, okay, here's my, Here's my XY plane. So here's the
Okay.
top half, here's the bottom half.
Oh, okay.
So I can only go this much.
Right.
See, if I'm on the x-axis, that would be, since I'm measuring this way, not the x-axis, sorry, the xy plane. If I'm on the xy plane, that means phi is 90 degrees or pi over 2. Does that make sense?
Mhm.
Because I went from here to there. Now, don't make me go more than that. I don't have the flexibility.
Mhm.
If I kept going, now I'm all the way down. That's pi. That throws people at first, but phi and theta are completely unrelated. Theta lives on the xy plane and just goes around in a circle. Phi is out in 3D, but I'm only measuring it. It'd be like saying I'm going to measure the angle to my wall. There's nothing on the other side of my wall to measure. So 0 to pi. Oh, here's my eraser. So the last piece, when we switch from rectangular to polar or cylindrical, we have that R in the R dr d theta. Okay. So in polar slash cylindrical, okay, dA becomes R dr d theta, dV becomes R dz dr d theta. In either case, we have the R. We derived that geometrically. I didn't tell you, we actually figured it out. There's a geometric derivation that's similar when I do spherical, but it's hard for me to do that in 2 dimensions. I did this last semester and I think I lost everybody. We're actually going to derive it differently next class. The derivation of the multiplier, like the R, we're actually going to derive next class. That's one of the major themes of next class. So today I'm going to tell you what it is and we're going to use it. So when I'm going from, now when I'm going spherical, okay, then there's no dA, it's only 3D. So my dV is going to become like this, rho squared sine phi. That's the piece that acts like the R does in polar. It's rho squared sine phi, d rho, usually it's d phi, d theta. That's the usual order you're going to go in. And the reason is your theta limits are always going to be constant. Rho is often bound by a function and sometimes phi is bound by a function, but theta will still be probably 0 to 2 pi most of the time. So this is the conversion in spherical. Now that looks absolutely terrifying, I know. But if a problem is meant to be done in spherical, it means that switching to spherical probably makes your integrand much friendlier. And it also means your limits of integration very well may all be constants, kind of like when you did it to polar. So we're going to do a really simple example. Let's find the volume of a sphere. A would be the radius of the sphere. Now, we kind of know what the answer is, but let's actually derive it using the spherical coordinates. So when I do this, I'm going to go right to the triple integral. Now, what we have to decide are what are our limits of integration. Now, it's a sphere. So clearly, theta is going all the way around. That's not even an issue. Okay, make sure you're muted. A lot of extra noise. It's a sphere, so I want the entire sphere. So my phi is going to go from 0 to pi. And finally, my rho is going to go from the center of the sphere, which would be 0, to the outer edge of the sphere, which would be a radius of A. So right off the bat, you notice all of my limits of integration ended up being constant, which is wonderful. Now, what's my integrand? This. Now, I do caution you, when you're making your phis and your thetas, most of us, myself included, are kind of lazy when we're drawing our thetas. You know, when there's only one angle and it's theta, you can't really mess it up or misinterpret it. So a lot of us, and myself, I'm guilty, you know, you kind of make a diagonal slash. You can't do that anymore, right? That's vertical, horizontal. If I'm ambiguous, I run the risk of misreading my own writing. And I see people do that all the time. They misread their thetas and their phis, and they're different animals. So just be mindful when you're making them. Okay, now my first integration is with respect to rho. So this is going to be 0 to 2 pi, 0 to pi, 1/3 rho cubed sine phi from 0 to a d phi d theta. And I evaluate the rho, so this will be 1/3 a cubed, okay? Sine phi d theta. Now I'm integrating the phi, so the antiderivative of the sine is the negative of the cosine, so I'll put the negative on the outside. 1/3 a cubed, cosine. I'm going from 0 to pi, and then d theta. Okay. So at this point, cosine of pi is -1 minus cosine of 0, which is 1, so that's -2. So I have 1/3 times -2, or I'll just write -2/3 a cubed d theta. Okay, again, cos theta, excuse me, cos pi minus 0, that's -2, but I already had a negative, so I'm good. That's a constant, so I can just multiply this by 2 pi. So my answer is going to be the negative of -2/3 a cubed times 2 pi, which I believe will be 4/3 pi a cubed. Right, that's what we were expecting. That's the volume of a sphere. But this derivation was actually quite simple. Okay, that's one of the nice things. So why would I ever use spherical coordinates? You would use spherical coordinates if you were integrating and your integrand was some version of x squared plus y squared plus z squared, perhaps raised to a power. So maybe I'm finding something and that's my density, x squared plus y squared plus z squared. Maybe I have the square root of x squared plus y squared plus z squared. Or I'm doing some sort of volume problem perhaps, and I'm bounded by a sphere, not a circular cylinder, but an actual sphere. I could use cylindrical coordinates on this. Spherical is easier. I can't use spherical coordinates if I actually had a circular cylinder. The problem that we just did, the can of cranberries, we could not have used spherical coordinates. It would have made it far too difficult because none of my limits would have been constant except for the theta limits. All right, let's do one more. And it's not the answer that I'm interested in, really, it's the setup. Because this, again, is very new, unexplored territory. All right, so imagine, if you will, and I have notes, by the way, there are notes online. So I have a sphere. All right, we got our sphere here. And from the center of the sphere, I've got a circular cone. Imagine, if you will, that I want to remove the circular cone, or that I want to find the volume of that piece of the cone. That's another thing. But it's not the circular cone, it's the circular cone with the ice cream on top. That's what that would be. If I wanted to find either the volume outside the cone, the volume inside the cone, the volume of just one of those pieces of the cone, that's a fairly simple spherical coordinates problem. Okay, this is not a complicated thing in general. So let's say my sphere is x squared plus y squared plus z squared equals a squared. Oops. And my cone, in case you don't realize, the equation of the cone would be z squared equals x squared plus y squared. Z squared equals x squared plus y squared is both halves. If it's only the top half, then it would be z equals the positive square root, because z equals the negative square root would be the bottom half, by the way. So a lot of folks don't realize that. This is top half only because there's no negative z's. This z can be positive or negative. So that's both halves. This is one half. Now, the question is, I know theta is going to go 0 to 2 pi. Whether I'm inside or outside, I know rho is going to go from 0 to a. So rho clearly is going to be 0 to a. That's easy. I know theta is going to be 0 to 2 pi. But what's phi going to be? Huh. In other words, if there's my z-axis, there's phi. What is that angle? Ooh, boy, that's That's not automatic unless you realize from here it actually is kind of automatic. Does anybody want to take a venture what that angle would be? Don't go by the accuracy of the drawing.
45.
It is.
45
Now,
degrees.
that depends entirely, by the way, on this guy. And here's what I mean. If I put a coefficient in front of either one of these, ooh, yeah, that was really loud. If I made that a 2x squared or a 3y squared, that changes everything. So how do I know it's 45 degrees? Because now if I think of projecting this onto a plane, I want to show you because everybody always asks the same question. How the heck am I supposed to figure out the phi? Now, first of all, I'm going to tell you what phi is. I'm going to erase this picture. My phi, well, it depends. Am I going from here to here or am I going from here to here? Well, if I'm going from here to here, it'd be 0 to pi over 4, because then that would be pi over 2, then that'd be 3 pi over 4, then that'd be back to pi. So this phi clearly is just going to be 0 to pi over 4. How the heck, okay? The answer was it was 45 degrees, but how are we supposed to figure that out? You're not going by the accuracy of my drawing. What you're going by is if I looked at a projection of this, a projection of this onto the XZ plane, that means that Y would be 0. So on the XZ plane, I would get two lines. I get the line Z equals X, and I get the line Z equals negative X. Does that make sense? Z would just be plus, Z would be basically the absolute value. Think of it that way, plus or minus. Oh, and I know that makes a 45 degree angle with here. Therefore, it also makes a 45 degree angle here. If I had a coefficient on this, then it wouldn't. In fact, this angle here is essentially inverse tan of 1. If I put coefficients on any of these, then it would be inverse tan of a different number. So when you're doing these problems, I promise you, I will always use coefficients of 1 so we can assume 45 degree angles. If that was not a 1, if that was a 2 or a 4 or just anything else, that's not 45 degrees anymore, because that line would have a, right, it'd be like that, be a much different angle. So
It would be a
this is
different
why.
problem if you try to solve the volume for the full kind of like hourglass shape or just the half. Would it be
Oh, you're talking about the inside of the cone?
yeah.
Oh,
So
okay.
it would be the inside, right? And then you have the bottom part too, which you said that would be Z squared, right? That's the full
Yes,
full
that's
cone.
how you know the difference. Let
Mhm.
me go back to my picture, because this is a question that comes up in spherical and in cylindrical. A common question is the role of symmetry. I'm a big symmetry guy. I taught geometry for years. I love everything about symmetry. Problem with symmetry is often misused. We often use it when we really can't. And so let me put the axes back in like I did before. So when I draw my cone, okay, that I think I just lost it. Anyway, all right. So there's a couple of questions here. I can say volume of the cone or the volume of the outside. The term I like to use is, I call it the bead. So if you think of a little round bead and you kind of hollow out the inside, I'm removing the cone. So the cone has a particular volume. This part here has a particular volume. And on the notes that I put, I actually drew the picture and kind of shaded it in. So when you're looking at the notes online, it's fairly easy to tell which part we're talking about because I've drawn the picture to go with the notes. Let's suppose I want to find this. Then phi is clearly 0 to pi over 4. But if I want to find this, then phi is going to be 3 pi over 4 to pi. So my question is, if I wanted to find both of these volumes, could I just find the top half and double it? What do you think? Anybody?
Yeah.
If I wanted to find the whole thing, could I just find one of them and double it?
I mean, if it's symmetrical, yeah, there's no coefficients that are, you
Yeah.
know, different. Yeah.
In fact, because both shapes are centered at the origin, I can. Now, what if I wanted to find the outer portion? Well, then what are my limits now? Now, from here to here, my phi limits would be pi over 4 to 3 pi over 4. And I can do that as just one simple integral. I don't need to do anything clever. The problem is I cannot do this and this as one integral because this is 0 to pi over 4, 3 pi over 4 to pi, the two different sets of intervals. So I would have to do two separate integrals or just use the fact that, you know what, it's exactly the same shape. So in polar and in spherical, symmetry really comes from when two shapes are congruent. Then I can find one and multiply. That's, do you guys remember in Calc 2 when you did the leaves? Do you guys remember doing things like that, sine 2 theta? And so you found, you know, these kind of things. Does anybody remember doing those kind of things?
Yeah.
Yes, no, anybody?
Yeah, I love flowers and
So nobody made four integrals. You made one integral and you multiplied it by 4 because all four of those would be exactly the same shape with the same area. And I can't do this as one integration because my intervals are all different. So what you did was we said, find all of the area bounded, you found one of them, you multiplied it by 4. That just makes sense. So in this case here, I don't go half and double. It's not like that. That doesn't work in this world. For this guy, I just need one integral, and that would be my phi limits. For this guy, I need one integral. If I want both, I just do one and then I double it. So here's a kind of a cool thing. We just found the volume of the whole sphere. What if you just found this one little piece right here, but you actually want this? Anybody want to tell me, how could I find that? How could I find this by finding this only?
well, you subtract the volume of the sphere from that particular volume that you find there.
Oh,
Oh,
wait, sphere minus
that. Sorry.
two of these. Now, what do you, it turns out the integration to find this and the integration to find this aren't much different. They're very similar in terms of the amount of work required. But I've often had it happen where a student will start a problem and go, oh, shoot, I was looking for the other thing. No, don't start over. Finish it and then just subtract it from the whole. You know, that's a nice little thing. Oh, yeah, that's right. I know the volume of the sphere. So this problem really is broken into a couple different ways. And this is one of the main types of problems that I like to deal with spherical because it's such a nice example. In general, spherical coordinates would be because I have a density that looks like a sphere, x squared plus y squared plus z squared, or I'm bounded by a sphere. If you're not bounded by a sphere, you probably don't want to use spherical coordinates. Trying to use spherical coordinates when you're not spherical in nature is really, really hard. But if I'm spherical in nature, spherical coordinates means my limits of integration are likely all to be constant. And man, that makes things so much easier. All right, so this is the last of the really, really weird, tricky stuff. Next day, the point of next day's lecture is we're actually going to do the mathematical justification of substitution. Every form of substitution you've ever done, whether it be a U sub, a trig sub, even a polar sub, even a spherical sub. Every substitution, we've always done substitutions and we got the answer. So the end justified the means. But kind of like when you derive derivatives using limits and you derive limits using epsilon delta, there must have been a justification as to why this was even valid in the first place. We're going to look at that next day. And it turns out it's a very powerful tool. It even involves some matrix algebra, which I will walk you through. Okay, it's not complicated, fairly simple stuff. Anyways, it's kind of neat. And then we start the end of the course, the part of the course that's called vector calculus. We did the calculus of vectors at the beginning of this course, you know, motion problems. The derivative of position is velocity. That's really low level derivative stuff. We're going to do something called vector calculus, which is a very, very different look. And I mentioned this on day one. The entire point of this course can be broken down into just one problem. I have a wheelbarrow. It's full of stuff. I want to get from point A to point B, and point A to point B might involve hills and curves, but it's definitely not linear. And as I'm moving along, stuff is falling out of my wheelbarrow. But there's a torrential downpour, so it's filling up with water. Oh, and there's got lots of leaks and holes, meaning the amount of weight that I'm pushing, the amount of force is changing continuously, and my path is all over the place. So starting from point A, getting to point B with variable force, question is, how much work did I get done? If you can answer that question, that encompasses almost everything you learn in Calc 3 in one question. And that is the point. That's what the vector calculus is. Then you think about it, where's there a vector in there? Well, there's actually lots of vectors in there. They're just, remember our position vectors? Yeah, those kind of vectors. Anyway, it's a good stopping